functions of two variables that would result in a three-dimensional shape. Okay, that's where we're going. So the idea behind the tangent line is that if you take a look at a function, you zoom in at a particular point, that function, this graph that looks all wavy like this, when you zoom in, it'll look like a line. And so that's the same idea for the function in 3 dimensions. So let me introduce you to my generic function. I'm going to draw this a lot. So you know in calculus 1, when somebody draws a generic function y is equal to f of x, they just kind of draw a wavy function off to the side. So this is like a 3-dimensional version of that. And what we're going to do is we're going to examine the derivatives with respect to x and with respect to y, the partial derivatives, and take a look at the geometry of the partial derivatives. So this is our function. Z is equal to f of x comma y. And then what we want to do is we want to take a look at a specific point on the domain. So your domain is on the xy plane. Let me randomly choose a point over here, and we'll call it AB. So when I write a point in 2 dimensions, I'm assuming that this is in the domain. But in 3 dimensions, this is actually A comma B comma 0, because it's on the xy plane. And so we have, corresponding to that, up on the surface, a point. And what's this point? What? F of AB would be the z value of it. And then the x and y values would just be, it's right above, right? So the shadow, so it has to be just AB. Okay? Now, I'm going to tear this up now. Maybe I'll recopy this. Too large to group. Is it too large to copy? All right. So what I'm going to do is, let's examine the derivative with respect to x. So let's do our analysis first with the derivative with respect to x. And we saw some simple computations numerically with a table. We saw another computation symbolically by just taking the derivative using symbols. And then we saw some level curve computations of this. So now let's actually look at the meaning of this with a graph. So fx is the derivative of the function with respect to x And what we're going to do is we're going to fix ourselves to a particular point, AB. So right on AB. So what you're doing is you're essentially looking for how the graph will change as you move along the x direction. And so you're on this mountain surface, and how are you going to change when you're in that direction? Okay? Now, to get a closer look at it, what I'm going to do is I'm going to cut this with a plane that's parallel to the xz plane. So let's take a look at that. I'm looking at this plane from the negative y-axis. So in 3 dimensions, pretend that you walk over here in the negative y-axis and you look at this plane. You look at the blue plane, and this is what you'll see, right? You're also going to see this intersection that the plane does with the surface. And so looking at it flat, just 2-dimensional, you might see something like this. That curve is the same as this curve right here. And then more specifically, if we focus on this dot, that would be somewhere over here. Now, if I look at this blue plane again, can you give me an equation for this blue plane? Close. Close. Y equals b, right? So y equals 0 is the xz plane. Y equals b has been shifted to some b level in the y. So this is actually the plane y equals b. So that plane y equals b cut. It cut the surface, and so all we see is a curve. Now, let's talk about this curve. This curve has a constant b. Right? So I'm going to express this curve as z is equal to f. This is the original f function, and I cut it with y equals b. So f of what? X is still variable, and then b made it fixed. So really, you can think about this as g1 of x. It's just a function of x, because it's not moving along the y. So if we look at that as g of x, we can just find the slope by doing g prime and then putting in the value of a Oh, I should have put a down here. This is x is equal to a, and then there's a point. So, since we know the derivative, well, like I said, this is just like a regular prime because it's really just a function of x. But we have to go back and pretend that it's a partial, so we'll do the partial derivative here. df dx of xb. So if I put in my x value, x equals a, then I'll get my slope. And my slope is equal to the partial of f with respect to x. Can I just, too much writing, f sub x? A, B. So that's when you plug in a after you've taken the derivative with respect to x. So that's a slope. Okay? Now, the thing is, I don't just want the slope. I actually want a vector out of this. So I actually want a vector and the magnitude of the vector doesn't matter as long as I have a vector. Because this is what we're looking for. Evan kind of laid it out for us. Find the derivatives and you find the vectors. That's a vector. This vector is tangent to the surface. And because it's tangent to the surface, it must be on the tangent plane. Now think about a smooth surface. And think about putting a plane, a flat plane on the surface, and then think about the vector going in the x direction. It'll be on that plane if it's tangent. So I want a vector that's tangent to the surface, and in this case I'm looking for a vector moving in the x direction. All right? So one way to get that vector is to look at this vector over here. So this red vector, okay, there's a red line there too. This red vector is the same thing as this red vector, except we're looking at this red vector on the right as something in 2 dimensions. And we can look at that red vector on the right as something in 2 dimensions because we know that it's not moving in the, it's not moving in the y direction. I put b there, that's wrong. If it's not moving in the y direction, what should it be? It should be 0. No movement in the y direction. So, yes?
Why do you need that
Oh, because the plan is to get a couple of tangent vectors that are tangent to the plane. I'm sorry, that's tangent to the surface. And if we cross those two vectors, we're going to get a normal vector, and so we can come up with an equation of a plane. Okay, so this is our first step. Our next step is to find another tangent vector, and then when we cross that, we're going to get a normal vector, and that normal vector is the vector that's going to help us create our plane. And all this, we're doing all this to find an equation of a tangent plane.
And why would we need to do that?
Oh, because back in Calc 1, we found the tangent line to help approximate things, linearization, and those kinds of things.
Wait, we aren't doing the unit.
Not necessarily. But I think there's a unitness to it.
So
So are we good here that I'm looking for this red vector and the middle component is 0 because I'm not moving in the y direction, so I'm just fixed in the y?
is that like the vector?
Okay? So now, we're fixing the y, we're dealing with x and z, and we have the slope. So what we're going to do is we can do a rise over run business to get the x and the z components. And we know that the rise over run is going to equal the slope. And then the rise looks like it's going to be your z component. And then your run is moving along the horizontal, which is your x component. So m is our slope. How are we going to negotiate the rise over run? Rise is equal to run times m. Not necessarily. I just want to find values. So here's the thing. Yeah. If you let x equal to 1, that's the run, then the z will have to equal to m. Does that make sense? 1, m. So those are the components of my vector. Yeah?
So would that make, since I might have this wrong, would that make it that vector over there,
This vector?
a unit vector?
No, not necessarily, because if m was like 2, and then x is 1, this would be 1, comma 0, comma something else. And the fact that it's something else will make it not a unit vector. Will make it not a unit vector. Yeah, aside from 0. So if this is anything else aside from 0, it's not a unit vector anymore. Yeah? No, they don't need to be unit vectors. They could be as long as you want, and in fact, your normal vector can be as long or as short as you want. All we want from that is the direction. Okay? We don't know what the hypotenuse is. You can get the hypotenuse by finding the length of the vector. So the hypotenuse is the length of the vector.
He's basically saying m equals m over 1.
Yeah, m equals m over 1. All right, cool. We got a vector. Wait, what's m? M is the partial. So our vector, what should we call it? V in the x direction. V sub x equals 1, 0, fx evaluated at AB. That's M, and we said this is M, so this must be M. Yeah.
How did we get that?
This? How do we get this?
Yes.
What we did was we looked at it from a flat point of view where we just have the x and z and we're not moving along the y because b is fixed or y is fixed. And so we got that set up to be just a function of x. We took the derivative of that function. Well, taking the derivative of that function, this is technically a function of two variables, so we actually had to take partials of that. And that's how we got this thing. Okay? Yeah, I know, it's a lot. It's getting exciting, though. Right? I'm excited. William? Yeah? The cross product, yes. Is that what you mean? Yeah. We'll do the cross product, and then the normal vector will make that into find the equation of a plane. So we'll do a couple of those from the last chapter. So we'll do a cross product, and we'll do a plane equation. So it's math is foundational. So the stuff that we learned last chapter, we'll continue to build on this. So that's what we're doing. All right. Let me put a box over here so I don't lose this. Not yet. So this is a vector. Here, let's specify what this vector is. This is a vector tangent to the surface, and I'll call my surface z is equal to f of xy. That's all we really need to know, but our additional information is the vector tangent to the surface at AB, f of AB, and it's going in the x direction. So it's not the normal vector yet, but it's one of the vectors that we need. And so we need to get another vector on the tangent plane so that we can cross them and get the normal vector. How's it look? All right, we're going to do the exact same thing. So I'm going to go a little bit faster on this one, okay? Or you can make it 2, but then your m has to be 2 times m. Or your rise has to be 2 times m. So 1 just seemed to be a nice number. It's semi-arbitrary. It just, like I said, if we put like 15 here, then that's the run, so the rise would have to be 15 times m, right? Because it has to satisfy this equation, rise over run. So whatever we make the run, we have to make the rise so that it's equal to m. So if we put 2 for the run, then this has to be 2m, so that 2's will cancel, and this is equal to m. So
if we in that problem, so if we were to multiply the run by 2, then we'd have to multiply the other side by 2, and that would be 2m instead of
Correct. Yeah. Yeah.
And same thing with the right, multiply the right.
Then you have to run by 2 also. Yeah. So why not just not multiply with anything and make the run equal to 1?
And can we do that all the time, or is it just like some?
I think if you're trying to match a specific slope, then that would be the key thing to do, to make it in 1. So I can't imagine this happening another time where we would make up another fraction like this. But if it comes up in class, then we'll talk about it. But I can't think about anything. So all the time for this one. Done?
Just to put some numbers for m, if m was like 6/5, for instance, then you would just know that your run the z change would be 6 and the x change would be 5. You just take that fraction and split it.
Yeah.
So it's not too bad. I think the algebra is a little weird on this.
Well, it's just algebra, and it's also because it's all just symbols and not actual numbers, like the example that you gave. Yeah. So yeah. So John just brought up the idea that what if it was m was equal to 6/5? Then it might be more natural to make the run equal to 5 and the rise equal to 6, right? But what I'm proposing is that we call this 1 and have the run equal to 6/5, which is the same thing, as long as it's the same. Okay? All right. Good. Good questions. Yes?
So for the y direction, it's just going to be 0, 1, f, y evaluated?
Yeah, you're just you're just stealing my thunder now. First Evan stole my thunder, and now you. It's all right. Yeah. Did you guys hear what he said? Okay. So I'll redevelop everything, and again, I'll go a lot quicker, and you'll see what Joe just said. It's 0, it is 0, 1, and Fy. Oh, actually, I think I drew that guy standing. I said that guy was standing in a negative y. I think he should have been standing in a positive y. Not that it matters anymore. This guy. Oh, does it look? It looks right, yeah. Yeah, that's right then. Yeah. Or left. X would be going the other way, yeah. Yeah, we don't need to do that. All right, so this time we have a plane. The plane, if you remember, was last time it was a y value. This time is going to be x is equal to a. That's the point. That's the x value, a, that we're going to cut it with. So we would be looking at, from this point of view, this is our curve, the YZ plane, yeah. Y, Z, and so this is your plane. X is equal to a this time, and we want to find a vector and so that vector will be on the plane, will be tangent to the surface, and will also be on the tangent plane. And then we'll get the slope again. We'll do the rise over run again. If we make the run equal to 1, your slope is equal to, this time you're moving along the y direction. So f sub y of AB is your m. And then you got the rise over run. The plane fixes this vector on the x. X is equal to a. It doesn't change. And so that's just going to be 0 in that component. We made the y value, the y direction, to be 1. And we made the z direction to be the rise, which is m. And so we have our vector v sub y to equal 0, comma 1, comma m, which is the partial with respect to y. So we did the same thing, right? Except we cut it along the y, moving along the y, so we're looking at the derivative with respect to y. X is fixed. And then we get it to this other vector. Yeah?
So we're doing the same thing along all three of the physical things?
No, just 2, because all we need is 2 vectors to cross, and then we got a normal.
So are we crossing those two vectors?
We're crossing this vector and the one on the previous page, yes.
Okay.
All right? We good? Yeah.
And x is fixed because we're actually on the x-axis.
X-axis is fixed because x is equal to a the whole time, and we're not moving along the a. So in terms of, we're just looking at the direction itself. We're not moving in the a direction, so our vector is not going to move in the a direction, so it has a 0 movement in the x direction.
You don't really want that line, right?
If you're going along x equals a, yeah. So you're on the x equals a plane. So this is the x equals a plane. Yeah, if you look at it straight down. Yep. Okay. Oh, this would have been a good time to do that 3D thing. The virtual reality. Damn. Oh, there's more. There's more 3D stuff. All right. Let's put it together. Change the colors. We're going to have the Vx vector in blue. And I'm going to temporarily leave out the parentheses AB there. We should understand that we're actually on AB. And then this other vector over here, called the Vy vector. I think that's what we call it. Wait. The first one's 1, 0. Yeah. And then if we cross it, we're going to get a normal vector. Now, depending on which way we cross it, we're either going to get this vector going up or the vector going down. It really doesn't matter which way we cross it. So let's cross it. Yeah, so one of these is what we're going to find, and we'll decide which it turns out to be after we cross it. I usually have a preference for this, but pick one. I'll let you guys pick. Vx cross Vy. I'll tell you if that was the one I wanted. It doesn't matter. I don't know. So x is 1, 0, fx. Y is 0, 1, fy. So the normal vector will be, so with respect to, it's in the I direction, it's 0 minus fx. In the y direction, it's negative fy minus 0. And then in the k direction, it'll be 1. I wanted it the other way. So that fx and fy are positive. But, like I said, it doesn't matter. Which one of these vectors did we find? Which one? The one going up or down? The one going down? Are you sure? So the z is positive, so it's going up into z. So this is the vector that we found. So Vx, Vx, Vy, right-hand rule pointing up, you'll also get that, the same result, if you use the right-hand rule. All right. Wait, what do we need? So we crossed it. What do we need for an equation of a plane? A point and a normal, right? What's our point? What's the point? What's the point? A comma B comma f of AB. How do you find the equation of a plane again?
Take the dot product of the normal vector and some regular point, and then that, whatever that is equal to the dot product of.
We want B, right? Uppercase B, which is the dot product of the normal. I thought it was the point on the plane.
Yeah, so this is this.
On the other side is the dot product of the normal vector.
So this is the point on the plane, right? And so if we dot this, our n is negative fx, and then I'll start putting the a, b. Let's not. Let's put it on. The x vector is x comma y comma z variables. So when I dot this, it'll be at negative fx times x plus negative fy times y plus 1 times z is equal to, now we have to dot this thing. D. Oh.
So that's the equation of the tangent plane?
Well, we're not quite done yet because we have to do this part.
So n tangent plane would be just the other constant d.
Yeah. There's another formula, I think, that I probably would have preferred here. Well, let me write this down. So minus fx of A and B, and this little dot here is times, scalar times. This is a plus, I think, right? All right. So let me solve for z, just for the heck of it. Because usually you're dealing with function z is equal to f of x, y, so, and this particular plane will end up being a function. Also, z is equal to something. So if we solve for z, and bring everything else to the other side, I'm going to connect these two, and I'll have a positive fx evaluated at, wait, sorry. Before I do that, I want to put this first, the f of ab. So let me put that first, f of ab, which is like the z value of the point, right? Plus, now if I bring this, the one that's underlined, over to the other side, fx, it'll be positive. And I'll combine it with this at the same time, which is negative. So this positive x and this minus a will be multiplied by fx. And I'll do the same with fy. Yeah?
And what is that regular A computation? That A that's here,
This one? Yeah, so this is like ab, f of ab, so f of ab is the point. It's the z component. This one?
no, that one right there. Just that two and
Right there?
besides that, the other A.
Oh, yeah, that's from multiplying this times a point. You know, this is this thing,
Oh, okay.
and it's these two being multiplied.
By the dot number?
Because we're dotting the normal and the point, this is what comes out when you dot the normal and the point.
Got it.
Okay? So these are the components that we took from that equation, moved it all to the right-hand side, and then we solve for z. That's our equation of the tangent plane. And I wrote it this way so that we might want to refer to this as a function in itself. And so if we just replace z with an f of xy, well, we're using f already for the function. Maybe we'll call it L of xy. Then we can see that this is a function of x and y that we can use. Okay. Nice. Now, think back to Calc 1. or Calc 2 if you want to take a look at Taylor polynomials. If this is your function and you have a point A here, and this is going to have a y value of f of A, right? And the slope is f prime of A, then the equation for this line is y minus y1 is equal to the slope times x minus x1. Let me see. This is equal to, y is equal to f of A plus f prime of A x minus A. Now look at that really carefully. Function of one variable, we have one derivative, right? And then now look at what we just did. So you should look at the similarities and see how much they are alike. Okay? Suppose we should do an example with actual numbers. So all we need for an example with actual numbers is a function and a point. So let's do that. So z is equal to what? Hyperbolic paraboloid, cone. Oh, cone has a square root. X squared plus y squared, so this is a regular paraboloid. All right. Now we need a point. 0, 0 is boring, so let's find another point. 3, 2. Okay? All right. Well, we really have the formula already. We don't have to go through this process anymore. And that's the whole point in math, is that you do this hard work by looking at these with generic symbols and variables. And all we really have to do now is plug it into the formula. So if this is A and this is B, we would try to figure out what the z component is, f of a, b. What is that? What is it? You put it in here, right? 9 plus 4. Or let's just say 3 squared plus 2 squared. So that's your f of AB. We need the derivatives. So fx is equal to what? 2x, right? So fx evaluated, now this is where we're going to actually get that number for to help us find the normal. Fx evaluated at 3, 2 is 2 times the x component, and there's no y, so we don't need to worry about the y, so we get 6 for that one. And similarly, we'll take the derivative with respect to y, put in your AB point. This time x doesn't play a factor, y is equal to 2, and then we're going to get that as your fy. Okay? So really, that's all you need. If I were to ask for the normal vector, you would tell me -6, -4, +1, and then you'd be done. Yeah?
Will we ever have to prove something like this on the exam?
No.
Or is it just it's something you can use?
I did it because it's fun for me. I could have just given you the formula. But I think seeing the process of how they got this formula is really, really interesting. All right. Now, just the formula, right? Z is equal to fx, x minus a. Oh, wait. F of AB. F of AB is 13. Fx, comma, or not comma, parentheses, x minus a, plus Fy, comma, y minus b. So this is it. Now you can move all the x, y, z's on the other side and then have it equal a constant to make it look like ax plus by plus cz is equal to d, which is how we're kind of used to seeing planes. But this works just as well as a plane. So here's the exciting part, to actually see it. So we have the surface. We can throw that point in there too. That's a 3, 2, comma 13. And then we'll put the plane in. Z is equal to 13 plus 6 times x minus 3 plus 4 times y minus 2. So we need to zoom in a little bit. Nope. Zoom out a little bit. Nope. We need to adjust this thing so that it includes, what's our point? 2, 3. So let's just go on the positive side. 0, comma 4, 0, comma 4. And then we went all the way up to 13, so I'll put 0, comma 20. Does it bother people that this isn't really a paraboloid looking thing? It's a piece of a paraboloid. If you guys buy that, then I'll leave it like that, so I don't have to try to make the graph look pretty. So you see that now we have a tangent, right? If we want to continue to explore other things like the normal vector, we can go from this point What was the normal vector again? 6, 4, and 6, 4, and minus 1, or -6, -4, +1, right? Okay. You know why it's not doing that? It's 8 times 8 is 16. So let's go 8. Minus 8. 8. I said 8. Minus 8. 8. Minus 8. 8. 0 to 16. I have to draw it so that it's so it's not being stretched one way or another. Now it looks like it's actually perpendicular. Now I think I can zoom out. Or, wait, I just zoomed in. Whatever. What's a good point of view? Right there, a little tilted. whatever. Okay? So now that we have that formula, we can just plug in the values. Just all it takes is to find the derivative. But I do expect you to be able to find other things like the normal vector, right? So the normal vector here, we decided to do this normal vector to be fx, fy, and -1. But the normal vector that we found, the z was +1. Remember? So if I ask for a normal vector going in a specific direction, then it's up to you to figure out whether this is +1 or -1, and then adjust your other derivatives accordingly. If I just ask for a normal vector, then it wouldn't matter which one you give me. Okay? So this tangent plane is used for linearization. It's used to help find differentials and those other things that are kind of interesting, but I don't really care to talk much about them. So I think this is maybe this is enough information for today. You guys can work on your homework. There's 2 homeworks due, right? 14.1 and 14.2. And then there's going to be the rest of Chapter 14 due on Tuesday, the labs for Chapter 14 due on Tuesday. All right, good luck. Oh, tests.